Hey there, my name is Daniel, and welcome to Soothing Science. Here we explore science slowly, without rushing, without pressure, and allow complex ideas to unfold at their own pace. If you find comfort in slow, thoughtful explorations of science, you might consider subscribing and spending more time here. For now, get comfortable, and let's begin. We stand on solid ground. This feels normal, ordinary even. But what holds us here? The answer seems simple at first. Gravity pulls us down. Everyone knows this. We learn it as children. We see it every time something falls, every time we jump and return to Earth, every time water flows downhill. The pattern is so constant, so reliable, that we stop thinking about it. But what is gravity exactly? Not what it does, but what it is. When we try to answer this question, the simple answer begins to dissolve. We might say it is a force that pulls objects together. We might say massive objects attract other objects. These statements are true in the sense that they describe what happens, but they do not explain why it happens, or how, or what gravity itself actually is. This turns out to be one of the hardest questions in all of science. Not because the mathematics are impossibly complex, though they can be. Not because experiments are difficult to perform, though they often are. The difficulty is deeper. Gravity does not fit neatly into our intuitive sense of how forces work. It behaves unlike anything else we encounter. And the more closely we examine it, the stranger it becomes. Tonight, we are going on a journey into this strangeness. We will move slowly, carefully, building our understanding piece by piece. We will start with what feels familiar and gradually work toward what is deeply unfamiliar. We will see how gravity shapes not just falling objects, but the structure of space itself, the flow of time, the formation of stars and galaxies, and the ultimate fate of the universe. Let us begin with something concrete. Drop a stone from shoulder height. It falls. We watch it accelerate downward, gaining speed until it strikes the ground. The entire event takes perhaps a second. In that single second, the stone has traveled about 1.5 meters. This is such an ordinary occurrence that we might not pause to consider what has happened, but consider this. The stone was at rest in our hand. Then it was moving. Something caused this change. We say gravity did it, but how? The stone is not touching the earth when it falls. There is only air between them. The earth is not pushing the stone from below because it is falling through empty space. The earth is not pulling the stone with any kind of rope or connection we can see. Yet the stone accelerates continuously in a specific direction. This is the first puzzle. Action without contact in most of our experience. When we want to change the motion of something, we touch it. We push a door. We pull a drawer. We throw a ball by making contact with it. Even when we think about invisible forces like magnetism, we can at least imagine field lines. Or we can feel the resistance when we push two magnets together. But gravity offers no such tangible experience. It acts across empty space, silently, invisibly, constantly. Now extend the puzzle. The moon orbits the Earth, held in its path by gravity. The distance between them is roughly 380,000 kilometers. That is nearly 10 times the circumference of Earth. Across this vast emptiness, gravity acts. The Earth somehow reaches out across this void and keeps the moon in orbit. And the effect is precise. The moon does not drift away. It does not spiral inward. It follows an elliptical path month after month, year after year with such regularity that ancient peoples used it to measure time. Extend further. The Earth orbits the Sun at a distance of 150 million kilometers. This is 150 million kilometers of mostly empty space, a few stray particles, occasional dust, mostly nothing. Yet across this distance, the Sun holds the Earth in a stable orbit. It has done so for billions of years. Every planet in the solar system is held in place this way. Mercury, closest to the Sun, feels a stronger pull. Neptune, 45 times farther from the Sun than Earth, feels a weaker pull. But it is enough to keep it bound in its orbit. The pattern becomes clear. Gravity acts across distance. It acts between any two objects with mass. The strength of this action depends on how much mass the objects have and how far apart they are. Double the distance, and the gravitational force becomes 4 times weaker. Triple the distance, 9 times weaker. This is called an inverse square law. It is a precise mathematical relationship, and it describes the behavior of gravity with remarkable accuracy. But knowing the pattern is not the same as understanding the mechanism. We can predict where the planets will be centuries from now using these mathematical rules. We can calculate the trajectory of a spacecraft with extraordinary precision. We can design satellites that orbit at exactly the right speed and altitude to remain stationary above a point on the equator. But none of this tells us what gravity is. For a long time, this bothered scientists. Isaac Newton formulated the law of universal gravitation in the 1600s, giving us the mathematical tools to describe gravitational interactions with great accuracy. But Newton himself was troubled by the question of mechanism. How does the Sun exert a force on the Earth across empty space? He famously declined to speculate, writing that he would not feign hypotheses. The mathematics worked. That would have to be enough, and for more than 2 centuries, it was enough. Newtonian gravity explained the motion of planets, the trajectories of comets, the tides in our oceans, the orbits of moons around other planets. It worked for nearly everything we could observe. The few anomalies that appeared minor, small discrepancies in the orbit of Mercury, strange behavior in the way light bent near the Sun. These were considered curiosities, puzzles to be solved within the existing framework. Then, in the early 20th century, Albert Einstein proposed a completely different way of thinking about gravity, not as a force, but as a curvature of space itself. This idea was so strange, so contrary to common sense, that it took years for the scientific community to accept it. Even today, more than a century later, it remains difficult to visualize. But it works. It explains things Newtonian gravity cannot, and it leads to predictions that have been confirmed again and again by experiment and observation. To understand what Einstein proposed, we need to think about space differently. We normally think of space as emptiness, the absence of things, a stage on which matter performs. This seems reasonable. Space itself does not push or pull. It does not heat or cool. It simply provides room for events to occur. But what if space is not passive? What if it has properties, structure, geometry? What if the presence of mass and energy causes space to bend, to curve, and objects moving through this curved space naturally follow curved paths? This is the core of Einstein's insight. Gravity is not a force pulling objects together. It is the curvature of space-time, and objects follow the straightest possible paths through this curved geometry. The word space-time is important. Einstein realized that space and time are not separate. They are woven together into a single 4-dimensional fabric. Events do not just occur at locations in space. They occur at specific moments in time. To describe where and when something happens, we need 4 numbers, 3 for position in space, 1 for position in time. Together, these 4 dimensions form spacetime. Mass and energy curve spacetime. The more mass, the more curvature. The Sun, with its enormous mass, creates a deep curvature in the spacetime around it. The Earth, moving through this curved spacetime, follows a curved path. We call this path an orbit, but from the Earth's perspective, it is moving in the straightest line possible, given the geometry of the spacetime it inhabits. It is not being pulled by a force, it is simply following the natural contours of curved spacetime. This explanation sounds abstract. We cannot see spacetime curvature directly. We cannot reach out and feel it. So how do we know it is real? The answer lies in predictions. Einstein's theory, called general relativity, predicts specific phenomena that Newtonian gravity does not. If we observe these phenomena, and if they match the predictions precisely, we have strong evidence that the theory describes reality. One prediction involves the bending of light. Light has no mass, so in Newtonian terms, gravity should not affect it. But light has energy, and energy contributes to the curvature of spacetime. When light passes near a massive object like the Sun, it follows the curved spacetime and its path bends. This can be observed during a solar eclipse, when stars near the Sun become visible. Their apparent position shifts slightly compared to where they appear when the Sun is not nearby. The shift matches Einstein's predictions with remarkable precision. Another prediction involves the orbit of Mercury. Mercury is the closest planet to the Sun, and it experiences the strongest gravitational effects. Its orbit is an ellipse, but the ellipse itself rotates slowly over time. This rotation, called the precession of the perihelion, could not be fully explained by Newtonian gravity. There was a small discrepancy, about 43 arcseconds per century. This might sound tiny, and it is, but it was measurable and unexplained. General relativity predicted exactly this amount of precession. The match was perfect. A third prediction involves time. In curved spacetime, time does not flow at the same rate everywhere. Clocks closer to a massive object run slower than clocks farther away. This effect is called gravitational time dilation. It has been measured directly using extremely precise atomic clocks. Place one clock on the ground and another on a mountaintop. The clock on the mountaintop, slightly farther from Earth's center and therefore in a region of weaker spacetime curvature, runs faster. The difference is tiny, measured in billionths of a second per day, but it is real, and it matches the predictions of general relativity. These confirmations are not isolated. Over the past century, general relativity has been tested in countless ways. Every test has either confirmed the theory or been within the margin of experimental uncertainty. The theory has never failed. This gives us confidence that spacetime curvature is not just a mathematical abstraction. It describes something real about the structure of the universe. But this raises a new question. If gravity is the curvature of spacetime, what exactly is being curved? We can visualize a curved surface, like the surface of a sphere or a saddle. But these are two-dimensional surfaces embedded in three-dimensional space. Spacetime is four-dimensional. What does it mean for four-dimensional spacetime to be curved? What is it curving into? The answer is subtle. Spacetime does not curve into anything. It curves intrinsically. This means the curvature is a property of the spacetime itself, not a result of it bending into some higher dimensional space. We can understand this through an analogy. Imagine beings living on the surface of a sphere, unable to perceive anything beyond that surface. They can still detect the curvature of their world by measuring distances and angles. If they draw a triangle on the sphere, the sum of its angles will be greater than 180 degrees. This reveals the curvature without requiring them to see the sphere from outside. Similarly, space-time curvature can be detected and measured by observing how objects move and how time flows without requiring space-time to be embedded in anything else. This intrinsic curvature is described mathematically using a framework called differential geometry. The details are complex, but the essential idea is that we can describe the geometry of space-time using measurements made entirely within space-time. We measure distances, angles, the way clocks tick, the paths objects follow. From these measurements, we construct a mathematical description of the curvature. This description tells us how space-time is shaped, and from that shape, we can predict how objects will move and how time will flow. The curvature of space-time is not uniform. It varies from place to place depending on the distribution of mass and energy. Near a massive object like a star, the curvature is strong. Far from any mass, in the depths of intergalactic space, the curvature is weak, nearly flat. But it is never exactly flat. Every bit of mass and energy, no matter how small, contributes some curvature. Even we, standing on Earth, curve the space-time around us. The effect is unimaginably tiny, far too small to measure with any existing instrument. But in principle, it is there. This leads to a profound realization. Gravity is not something that mass exerts. It is something that mass is. The presence of mass warps the geometry of space-time, and that warping is what we experience as gravity. There is no separate gravitational force being transmitted from one object to another. There is only the shape of space-time, and the natural tendency of objects to follow the straightest paths through that shape. Now let us slow down and consider what this means for falling objects. When we drop a stone, we say it falls because of gravity. But in the framework of general relativity, the stone is not falling. It is following a straight path through curved space-time. From the stone's perspective, nothing is pulling it. It moves freely, experiencing no force. The ground, however, is not moving freely. The surface of the Earth is being pushed upward by the electromagnetic forces between atoms in the solid Earth. These forces prevent the surface from following its natural geodesic, which would be to fall inward toward the center. So in a very real sense, we are not at rest on the surface of the Earth. We are constantly accelerating upward, held aloft by the structure of matter beneath us. This might sound backward. We feel like we are being pulled down, not pushed up. But what we feel is not gravity. What we feel is the resistance of the ground pushing against us, preventing us from following our natural path through space-time. If we were truly in free fall, falling toward the Earth with nothing to stop us, we would feel weightless. Astronauts in orbit experience this weightlessness not because there is no gravity, but because they are in free fall, following a natural geodesic through curved space-time without anything pushing against them. This perspective shift is disorienting at first. It asks us to reconsider something so fundamental that we rarely think about it. But it resolves many paradoxes. It explains why all objects fall at the same rate, regardless of their mass. A feather and a hammer, dropped in a vacuum on the moon, hit the ground at the same time. This puzzled scientists for centuries. If gravity is a force, why does it not affect heavier objects more strongly? But if gravity is the curvature of space-time, then all objects follow the same geodesics, the same natural paths through the curvature. Mass does not determine how fast something falls. It only determines how much that object itself contributes to the overall curvature. The universality of freefall, as this principle is called, has been tested with extraordinary precision. Experiments have compared the fall rates of objects made from different materials with different compositions and masses. The results always agree to within the experimental limits. Some experiments have measured agreement to better than 1 part in a trillion. This universality is one of the strongest confirmations of the equivalence principle, the foundation of general relativity. Let us now turn our attention to the flow of time. We usually think of time as universal, flowing at the same rate everywhere. 1 second here is the same as 1 second there, but general relativity tells us this is not true. Time is part of space-time, and just as space curves in the presence of mass, time dilates. Clocks in different gravitational environments tick at different rates. Consider two observers, one standing on the surface of the Earth and another floating far out in space, far from any significant mass. Each has an identical clock. To the observer in space, their clock ticks normally, measuring seconds in the usual way, but when they observe the clock on Earth, they see it ticking more slowly. Time on Earth runs slower than time in deep space. The difference is small for Earth's gravity, but it is measurable. For every year that passes in deep space, slightly less time passes on Earth's surface. The difference amounts to about 1 part in a billion. Over a human lifetime, this adds up to a fraction of a second. But it is real. The effect becomes much stronger near more massive objects. Near a neutron star with its intense gravitational field, time slows dramatically compared to time far away. A clock on the surface of a neutron star would tick noticeably slower, perhaps half as fast as a clock in deep space. Near a black hole, the effect becomes extreme, close to the event horizon. Time nearly stops from the perspective of a distant observer. Light emitted from near the event horizon is redshifted, stretched to longer wavelengths. Because time is passing so slowly there, events that take seconds for someone near the black hole might appear to take hours or days for someone watching from a safe distance. This is not an illusion. It is not a trick of perception. Time genuinely flows at different rates in different parts of space-time. This has practical consequences. The global positioning system, which uses satellites orbiting Earth to provide location information, must account for both gravitational time dilation and the effects of special relativity. The satellites orbit at high altitude, where gravity is weaker, so their clocks run faster than clocks on the ground. They also move at high speeds, which causes their clocks to run slower according to special relativity. The two effects partially cancel, but not completely. The net result is that satellite clocks gain about 38 microseconds per day relative to ground-based clocks. If this were not corrected, GPS positions would drift by several kilometers per day. The system works only because the engineers account for the predictions of relativity. Time dilation also means that gravity affects light. Light is electromagnetic radiation, oscillating at a particular frequency. When light climbs out of a gravitational well, moving from a region of strong curvature to a region of weak curvature, it loses energy. This energy loss appears as a decrease in frequency, a shift toward the red end of the spectrum. This is called gravitational redshift. It has been measured in laboratory experiments, comparing light emitted from the top and bottom of tall towers. The frequency difference is tiny, but modern atomic clocks are precise enough to detect it. Now we arrive at one of the most remarkable predictions of general relativity: the existence of black holes. A black hole is a region of space-time where the curvature becomes so extreme that nothing, not even light, can escape. This happens when a massive amount of matter is compressed into an incredibly small volume. The curvature of space-time becomes so steep that all paths lead inward. There are no outward geodesics. Once something crosses a boundary called the event horizon, it cannot return. Black holes were initially viewed as mathematical curiosities, solutions to Einstein's equations that might not correspond to anything real. But over time, evidence accumulated. Astronomers observed stars orbiting invisible companions, companions with masses far too large to be ordinary stars, yet emitting no light. They observed jets of matter being ejected from the centers of galaxies, powered by something with enormous mass, confined to a tiny region. They observed gravitational waves, ripples in spacetime produced when black holes collide and merge. All of this pointed to the reality of black holes. In recent years, the evidence has become even more direct. The Event Horizon Telescope, a global network of radio telescopes working together, captured an image of the shadow of a black hole at the center of the galaxy M87. The image shows a bright ring of light surrounding a dark region. The dark region is the shadow of the event horizon, a silhouette where the black hole blocks light from behind it. The size and shape of this shadow match the predictions of general relativity with stunning accuracy. This is as close as we can come to seeing a black hole directly. Black holes challenge our intuition in profound ways. Inside the event horizon, the roles of space and time exchange. Moving forward in time becomes like moving toward the center. There is no escape, just as we cannot escape moving forward in time. The singularity at the center, where all the mass is compressed to infinite density, represents a boundary of the theory. General relativity predicts its existence but cannot describe what happens there. The mathematics break down. Infinities appear. This suggests that general relativity, as successful as it is not the final answer. At the smallest scales and highest densities, a deeper theory is needed. But this does not diminish the achievement of general relativity within its domain of validity, which encompasses nearly everything we can observe. It works brilliantly. It describes the bending of light, the precession of orbits, the slowing of time, the existence of black holes, and the expansion of the universe itself. Each prediction has been tested and confirmed. The theory stands as one of the greatest intellectual achievements in human history. Let us now consider gravity on the largest scales. When we look out into the universe, we see galaxies scattered through space. These galaxies are not distributed randomly. They cluster together, forming groups and superclusters, connected by filaments of matter with vast voids in between. This structure is shaped by gravity. Over billions of years, gravity has drawn matter together, amplifying small initial irregularities into the cosmic web we observe today. The process began shortly after the Big Bang. At that time, the universe was nearly uniform, but not perfectly so. There were tiny variations in density, about 1 part in 100,000. In regions that were slightly denser than average, gravity pulled in more matter. This made those regions denser still, which strengthened their gravitational pull, which attracted even more matter. This feedback process, called gravitational instability, gradually built up structure. Over millions and billions of years, small overdensities grew into galaxies, clusters of galaxies, and the vast cosmic web. Gravity also determines the fate of individual galaxies. Within a galaxy, stars orbit the galactic center, held in place by the combined gravity of all the matter in the galaxy. The Milky Way, our home galaxy, contains hundreds of billions of stars, along with gas, dust, and dark matter. All of this mass curbs space-time, creating a gravitational well that keeps the galaxy bound together. Stars near the edge of the galaxy orbit slowly, taking hundreds of millions of years to complete one orbit. Stars closer to the center move faster. Our Sun, located about halfway out, takes roughly 230 million years to orbit the galactic center. This orbital period is sometimes called the galactic year. But there is a puzzle. When astronomers measure the speeds of stars and galaxies, they find something unexpected. Stars far from the galactic center are moving faster than they should be, given the amount of visible matter. According to the laws of gravity, whether Newtonian or relativistic. Stars at large distances should orbit more slowly, but they do not. Their speeds remain roughly constant even at great distances from the center. This suggests there is more mass in galaxies than we can see. This unseen mass is called dark matter. Dark matter does not emit or absorb light. It does not interact with electromagnetic radiation in any way we have detected. But it has mass, and therefore it curves spacetime. Its gravitational effects are clear. We see them in the rotation curves of galaxies. We see them in the way light bends around galaxy clusters. We see them in the patterns of the cosmic microwave background, the afterglow of the Big Bang. All of this evidence points to the existence of a form of matter that interacts primarily through gravity. We do not know what dark matter is. It might be a new kind of particle, something not part of the standard model of particle physics. It might be massive compact objects, like black holes or other dense remnants that do not emit light. Or it might be something else entirely. Experiments are underway to detect dark matter directly, to create it in particle accelerators, to observe its effects more precisely. So far, it remains elusive. But its gravitational influence is undeniable. Without dark matter, galaxies as we observe them would not hold together. Stars would fly apart. The structure we see in the universe would not exist. Dark matter makes up about 85% of all matter in the universe. This means that everything we can see, all the stars and galaxies and gas and dust, represents only 15% of the total matter. The rest is dark, interacting with ordinary matter only through gravity. This is a humbling realization. The universe is mostly made of something we cannot see and do not understand. There is also dark energy, which is stranger still. Dark energy is not a form of matter. It is a property of space itself, a kind of energy density that fills all of space-time. Its effect is to cause the expansion of the universe to accelerate. This acceleration was discovered in the late 1990s by observing distant supernovae. These exploding stars serve as standard candles, objects with known intrinsic brightness. By measuring how bright they appear from Earth, we can determine their distance. By measuring how much their light has been redshifted, we can determine how fast they are moving away from us. When astronomers did this for many supernovae, they found that the most distant ones were farther away than expected. The universe was not just expanding, it was expanding faster and faster. This was completely unexpected. Gravity is attractive. It should slow the expansion, pulling galaxies back toward each other. For the expansion to accelerate, there must be something with repulsive gravitational effects. Dark energy provides this repulsion. It acts like a negative pressure, pushing space apart. The more space there is, the more dark energy there is, which causes even faster expansion. This creates a runaway process. As the universe expands, the amount of dark energy increases, which drives faster expansion, which creates more space, which contains more dark energy. Dark energy makes up about 68% of the total energy density of the universe. Dark matter makes up about 27%. Ordinary matter, everything made of atoms, makes up only about 5%. We live in a universe dominated by things we do not understand. Dark matter and dark energy are detected only through their gravitational effects. They remain among the deepest mysteries in physics. The presence of dark energy has profound implications for the future of the universe. If dark energy continues to drive accelerated expansion, galaxies will move farther and farther apart. Eventually, distant galaxies will recede so fast that their light can never reach us. The observable universe will shrink. Billions of years from now, an observer in the Milky Way might see only our local group of galaxies. Everything else will have disappeared beyond the horizon, carried away by the expansion faster than light can travel. The universe will seem empty, dark, cold. On even longer timescales, stars will exhaust their fuel and die. New stars will form more slowly as gas and dust are consumed. Eventually, star formation will cease entirely. The universe will contain only remnants, white dwarfs, neutron stars, black holes. These remnants will themselves decay over unimaginable spans of time. Protons may decay. Black holes will evaporate through Hawking radiation. In the end, if dark energy persists, the universe will approach a state of maximum entropy, a cold, diffuse, nearly empty expanse with no structure, no complexity, no possibility of life. This is one possible future, but it rests on assumptions. We assume dark energy remains constant. We assume general relativity continues to hold on cosmic scales. We assume no new physics intervenes. These are reasonable assumptions given current evidence, but they are not certainties. The universe has surprised us before. It may surprise us again. Let us return to something closer to home. Gravity shapes not only the cosmos, but also the everyday world around us. It determines the structure of planets, the behavior of atmospheres, the flow of water. Without gravity, Earth would not exist. The matter that formed our planet was drawn together by gravity during the early days of the solar system. A cloud of gas and dust left over from the formation of the sun began to clump together. Small particles collided and stuck. Over time, these grew into larger bodies called planetesimals. Gravity pulled these planetesimals together, and eventually, they formed planets. As Earth grew, gravity compressed its interior. This compression generated heat. The heat melted rock and metal, allowing the planet to differentiate. Heavy elements, mostly iron and nickel, sank toward the center, forming the core. Lighter materials rose to form the mantle and crust. This process created the layered structure we see today. The core remains hot, partially molten, generating Earth's magnetic field. The mantle convects, driving plate tectonics. The crust floats on the mantle, constantly reshaped by volcanic activity, erosion, and the slow drift of continents. Gravity also holds Earth's atmosphere in place. Gas molecules move quickly, bouncing around in random directions. Without gravity, they would escape into space. But Earth's gravity pulls them downward, confining them to a thin layer near the surface. The thickness of this layer depends on the balance between gravity and the thermal energy of the molecules. The stronger the gravity, the thinner the atmosphere. The hotter the atmosphere, the thicker it becomes. For Earth, with its moderate gravity and temperature, the atmosphere extends several hundred kilometers above the surface, though most of the mass is concentrated in the lowest 10 kilometers. Gravity determines atmospheric pressure. The weight of the air above presses down on the air below. At sea level, this pressure is about 100,000 pascals, enough to support a column of mercury 76 centimeters high. As we ascend, there is less air above, so the pressure decreases. At the summit of Mount Everest, the pressure is about 1/3 of sea level. At the edge of space, it is nearly zero. Water, too, is governed by gravity. Rain falls because gravity pulls water droplets downward. Rivers flow downhill, carving valleys and canyons. Oceans settle into the lowest elevations, forming vast basins. The tides, those slow oscillations of sea level, are caused by the gravitational pull of the moon and sun. The moon, being closer, has a stronger effect. It creates a bulge in the ocean on the side of Earth facing the moon, and another bulge on the opposite side. As Earth rotates beneath these bulges, the sea level at any given location rises and falls, typically twice per day. Even our bodies are shaped by gravity. Our bones are strong enough to support our weight against the pull of Earth's gravity. Our muscles work constantly to keep us upright. Our cardiovascular system pumps blood against gravity, ensuring that our brains receive oxygen even though they are elevated above our hearts. If we spend extended periods in low gravity, as astronauts do in orbit, our bodies adapt. Bones lose density. Muscles weaken. The heart, no longer working as hard, loses some of its strength. These changes are reversible, but they highlight how profoundly gravity influences biological systems. Gravity is also essential for life in a broader sense. Stars exist because of gravity. The sun formed when a cloud of gas collapsed under its own weight. As the cloud contracted, it heated up. Eventually, the temperature and pressure at the core became high enough to ignite nuclear fusion. Hydrogen nuclei fused into helium, releasing energy. This energy generates the light and heat that sustain life on Earth. Without gravity, the sun would not exist. Without the sun, Earth would be a frozen, lifeless rock. The balance between gravity and the outward pressure from nuclear fusion determines the lifespan and evolution of stars. A star like the sun will shine for about 10 billion years. Larger stars burn faster and die sooner. Smaller stars burn slower and last longer. At the end of their lives, stars either explode or collapse. In both cases, gravity plays a central role. When fusion stops, there is nothing to support the star against its own gravity. It collapses. If the star is massive enough, the collapse can trigger a supernova, a catastrophic explosion that outshines entire galaxies for a brief time. The remnants of these explosions are scattered into space, enriching the interstellar medium with heavy elements. These elements, forged in the cores of dying stars, eventually become part of new stars, planets, and life. We are made of stardust, material recycled through stellar birth and death, processes driven by gravity. If the collapsing core is massive enough, not even the pressure of neutrons can stop it. It continues collapsing, shrinking past the event horizon, becoming a black hole. This is one of the endpoints of stellar evolution. Another endpoint is a neutron star, where the collapse is halted by neutron degeneracy pressure. Neutron stars are incredibly dense, packing more mass than the sun into a sphere about 20 kilometers across. Their surfaces have intense gravitational fields, strong enough to warp space-time noticeably. Light emitted from a neutron star is gravitationally redshifted. Time runs slower there. An observer on the surface would age more slowly than someone far away. Now let us consider one of the most dramatic predictions of general relativity: gravitational waves. When massive objects accelerate, they create ripples in spacetime that propagate outward at the speed of light. These ripples are gravitational waves. They carry energy away from the system that produced them. Unlike electromagnetic waves, which require electric charges, gravitational waves are produced by masses in motion. Any accelerating mass generates them, but the effect is incredibly weak unless the masses are enormous and moving very quickly. The strongest sources of gravitational waves are cataclysmic events, colliding black holes, merging neutron stars, supernovae, the rapid rotation of asymmetric neutron stars. Even these generate waves so faint that they are extraordinarily difficult to detect. As a gravitational wave passes through Earth, it stretches and compresses space by an infinitesimal amount. The change in distance is far smaller than the width of an atomic nucleus over distances of kilometers. Detecting such tiny distortions requires instruments of astonishing precision. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, achieved this feat in 2015. LIGO consists of two detectors, one in Louisiana and one in Washington state. Each detector is an L-shaped vacuum chamber with arms 4 kilometers long. Laser beams travel down the arms, bounce off mirrors, and return. By comparing the time it takes light to travel each arm, the detector can measure changes in length with extraordinary sensitivity. When a gravitational wave passes, one arm stretches while the other compresses. The effect is tiny, but measurable. On September 14, 2015, both LIGO detectors registered a signal. The signal lasted a fraction of a second. It matched the predicted pattern from 2 black holes spiraling together and merging. One black hole had about 36 times the mass of the Sun. The other had about 29 times the Sun's mass. They orbited each other, moving faster and closer until they collided and merged into a single black hole with about 62 times the Sun's mass. 3 solar masses worth of energy was radiated away as gravitational waves during the final moments of the merger. This energy, released in a fraction of a second, was greater than the light output of all the stars in the observable universe combined. Since that first detection, LIGO and other gravitational wave observatories have detected dozens of mergers. Each detection confirms the predictions of general relativity. The shape of the waveforms, the wave frequency increases as the objects spiral inward, the sudden ring down as the merged object settles, all match the theory's equations. Gravitational waves have opened a new window onto the universe. They allow us to observe events that produce no light, to study the most extreme environments where gravity is at its strongest, and to test general relativity in regimes never before accessible. We have now explored gravity across many scales and contexts, from falling stones to orbiting planets, from the slowing of time to the expansion of the universe, from the formation of stars to the collision of black holes. Gravity shapes everything. It is the architect of cosmic structure, the sculptor of spacetime, the force that determines the fate of matter and energy across all of existence. Yet despite this deep understanding, mysteries remain. We do not know what dark matter is. We do not know what dark energy is. We do not know how to reconcile general relativity with quantum mechanics, the other great pillar of modern physics. At very small scales, quantum effects dominate. Particles behave probabilistically. The smooth curvature of space-time described by general relativity seems incompatible with the jittery, uncertain nature of the quantum world. A complete theory of quantum gravity, one that unifies these two frameworks, remains elusive. String theory, loop quantum gravity, and other approaches attempt to bridge this gap. Each offers tantalizing possibilities, but none have yet produced testable predictions confirmed by experiment. The quantum nature of gravity might only manifest in extreme conditions, inside black holes, during the first moments of the Big Bang, at energy scales far beyond what we can create in laboratories. This makes progress difficult. We are like explorers mapping a continent from its shores, unable to see inland, forced to infer the landscape from indirect clues. But the search continues. Physicists probe the limits of the theories, looking for cracks, for hints of deeper structure. Astronomers observe the universe with ever more sensitive instruments, searching for anomalies that might reveal new physics. Experimentalists push the boundaries of measurement, testing the predictions of relativity with greater precision, hoping to find deviations that point toward something beyond. This is the nature of science. Each answer leads to new questions. Each solved mystery reveals deeper mysteries. Gravity, for all we have learned about it, still holds secrets. And perhaps that is fitting. The quiet force that shapes everything, that bends space, slows time, and draws all matter together, resists our final understanding. It invites us to keep looking, keep questioning, keep seeking the deeper truth beneath the surface of the familiar. We stand on solid ground, held by gravity, warmed by a star sustained by gravity, part of a galaxy bound by gravity, within a universe shaped by gravity. And we wonder, what is this force that seems so simple yet defies complete comprehension? What is the nature of spacetime? What lies at the singularity of a black hole? What will be the ultimate fate of the cosmos? These questions connect us to the generations of thinkers who came before, who looked up at the night sky and asked why things fall, why planets move, what holds the universe together. They connect us to the future, to those who will build on what we know, who will uncover truths we cannot yet imagine. Gravity, the quiet force that shapes everything, continues to shape our understanding, our curiosity, our place in the vast unfolding mystery of existence. But to truly appreciate the depth of this mystery, we need to look more closely at what happens when gravity becomes extreme, when matter concentrates to such densities that space-time itself undergoes radical transformation. Consider a white dwarf star. This is what remains after a star like our Sun exhausts its nuclear fuel. The fusion reactions that once held the star up against its own gravity cease. The core collapses, but the collapse does not continue indefinitely. At a certain density, the electrons in the star resist further compression through a quantum mechanical effect called electron degeneracy pressure. This is not thermal pressure, not the pressure of particles bouncing around in thermal motion. It is a consequence of the Pauli exclusion principle, which states that no two electrons can occupy the exact same quantum state. When matter is compressed to extreme densities, electrons are forced into higher and higher energy states, and this creates an outward pressure that can balance gravity. A white dwarf is extraordinarily dense. A teaspoon of white dwarf material would weigh several tons on Earth, yet it is stable. It sits in equilibrium, neither collapsing further nor expanding. It cools slowly over billions of years, radiating away its residual heat, gradually fading to a cold, dark remnant. This is the likely fate of our Sun and of most stars in the universe. But there is a limit to how much mass a white dwarf can contain. This limit, called the Chandrasekhar limit, is about 1.4 times the mass of the Sun. If a white dwarf accumulates more mass than this, perhaps by pulling material from a companion star, electron degeneracy pressure can no longer support it. The star collapses again. The collapse is sudden and violent. Within seconds, the temperature and pressure become so extreme that carbon and oxygen in the star undergo runaway nuclear fusion. The entire star explodes in a type Ia supernova, releasing as much energy in a few weeks as the Sun will emit over its entire lifetime. These supernovae are important for cosmology because they have remarkably consistent peak brightness. This makes them excellent standard candles for measuring distances across the universe. It was observations of distant type Ia supernovae that revealed the accelerated expansion of the universe and led to the discovery of dark energy. Now consider what happens if the collapsing core of a massive star exceeds a different threshold. If the core has more than about 2 to 3 solar masses, even neutron degeneracy pressure cannot halt the collapse. Neutrons, like electrons, obey the Pauli exclusion principle, and at extreme densities they resist compression. But if the mass is too great, this resistance is insufficient. The core continues collapsing. There is no known force or pressure that can stop it. The matter falls inward, compressing into a region of smaller and smaller radius until it crosses the event horizon and becomes a black hole. The event horizon is not a physical surface. It is a boundary in space-time, a point of no return. Once crossed, all possible future paths lead inward. Light emitted from inside the event horizon cannot escape, not because it lacks energy, but because the geometry of space-time does not permit outward trajectories. The escape velocity, exceeds the speed of light. And since nothing can travel faster than light, nothing can escape. From the outside, a black hole appears black, hence the name. It emits no light. But its presence can be detected through its gravitational effects. If a black hole is part of a binary system, orbiting a normal star, it can pull gas from that star. The gas spirals inward, forming an accretion disk. As the gas falls toward the event horizon, it heats up through friction and compression, reaching temperatures of millions of degrees. At these temperatures, it emits X-rays. We can detect these X-rays and infer the presence of the black hole. We can also detect black holes by observing the motion of nearby stars. At the center of the Milky Way, astronomers have tracked stars orbiting an invisible object. These stars move at incredible speeds, thousands of kilometers per second, following elliptical orbits with periods ranging from a few years to decades. By measuring their orbits, we can calculate the mass of the central object. It turns out to be about 4 million times the mass of the Sun, confined to a region smaller than the orbit of Mercury. The only object that can have this much mass in such a small volume is a black hole. This supermassive black hole, known as Sagittarius A, sits at the heart of our galaxy. Nearly every large galaxy has a supermassive black hole at its center. These black holes contain millions or even billions of solar masses. How they formed remains an open question. They may have grown from smaller black holes that merged over time. They may have formed directly from the collapse of massive gas clouds in the early universe. Whatever their origin, they play a crucial role in galactic evolution. The energy released by matter falling into these black holes can drive powerful jets and winds that regulate star formation throughout the galaxy. Inside the event horizon, our understanding breaks down. General relativity predicts that all the mass collapses to a point of infinite density called a singularity. At this singularity, the curvature of spacetime becomes infinite. The equations produce infinities, which is a sign that the theory has reached its limit. We do not know what actually happens at the singularity. General relativity cannot tell us. A quantum theory of gravity might provide an answer, but we do not yet have such a theory. There are hints, however. In the 1970s, Stephen Hawking applied quantum mechanics to the region just outside the event horizon and discovered something remarkable. Black holes are not entirely black. They emit radiation. This radiation, now called Hawking radiation, arises from quantum fluctuations in the vacuum near the event horizon. Particle-antiparticle pairs spontaneously appear and annihilate throughout empty space. Normally, this has no observable effect, but near the event horizon, one member of a pair can fall into the black hole while the other escapes. To an outside observer, it appears that the black hole is emitting particles. Hawking radiation carries energy away from the black hole. This means the black hole loses mass over time. It evaporates. For a black hole with the mass of the Sun, this evaporation takes an unimaginably long time, far longer than the current age of the universe. But smaller black holes evaporate faster. A black hole with the mass of a mountain would evaporate in about the age of the universe. A black hole with the mass of a large asteroid would evaporate in seconds, releasing an enormous burst of energy. This prediction has profound implications. It means black holes are not eternal. Given enough time, they will disappear. It also suggests a deep connection between gravity, quantum mechanics, and thermodynamics. Black holes have entropy, a measure of disorder. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This is strange and hints at something fundamental about the nature of information in spacetime. The information paradox arises from this. When matter falls into a black hole, it carries information with it. information about the quantum state of the particles, their positions, momenta, spins, and so on. If the black hole evaporates completely through Hawking radiation, what happens to this information? Hawking radiation appears to be thermal, random, carrying no information about what fell in. This seems to violate a fundamental principle of quantum mechanics, which says information cannot be destroyed. The resolution of this paradox remains unclear. Some physicists believe the information is somehow encoded in the Hawking radiation in a subtle way we do not yet understand. Others propose more radical ideas, such as the holographic principle, which suggests that all the information about the interior of a black hole is encoded on its event horizon. Let us step back from black holes and consider the universe as a whole. The fact that the universe is expanding is itself a consequence of general relativity. In the 1920s, observations by Edwin Hubble showed that distant galaxies are moving away from us. The farther away a galaxy is, the faster it recedes. This is not because galaxies are moving through space away from us. It is because space itself is expanding, carrying galaxies along with it. Einstein's equations applied to the entire universe predict this expansion. In fact, Einstein initially found this result troubling. He believed the universe should be static, neither expanding nor contracting. To achieve a static solution, he added a term to his equations called the cosmological constant. This term represents a kind of energy inherent to space itself, a repulsive effect that could balance the attractive force of gravity and keep the universe static. But the universe is not static. When the evidence for expansion became undeniable, Einstein reportedly called the cosmological constant his greatest blunder. Ironically, the cosmological constant has returned in modern cosmology as a possible explanation for dark energy. The equations allow it, and observation suggests that something very much like it exists, driving the accelerated expansion we observe today. The expanding universe has a history. If we trace the expansion backward in time, galaxies were closer together in the past. Go back far enough and all the matter and energy in the universe was compressed into an incredibly hot, dense state. This is the Big Bang. It is not an explosion in space, it is an expansion of space itself. Time and space began with the Big Bang. Or at least our current understanding of physics cannot describe what, if anything, came before. In the first fractions of a second after the Big Bang, the universe was extraordinarily hot and dense. Temperatures exceeded trillions of degrees. Matter, as we know it, could not exist. Instead, there was a seething plasma of fundamental particles and radiation. As the universe expanded, it cooled. Within the first few minutes, protons and neutrons combined to form the lightest atomic nuclei, hydrogen, helium, and trace amounts of lithium. This process, called Big Bang nucleosynthesis, produced the raw material for the first stars. For the next few 100,000 years, the universe was opaque. Photons scattered constantly off free electrons, unable to travel far. But as the universe continued to expand and cool, eventually the temperature dropped enough for electrons to combine with nuclei, forming neutral atoms. This is called recombination. With the electrons bound into atoms, photons could travel freely. The universe became transparent. The light from this era has been traveling through space ever since. We detect it today as the cosmic microwave background, a faint glow of radiation coming from all directions. The cosmic microwave background is remarkably uniform, with a temperature of about 2.7 degrees above absolute zero. But it is not perfectly uniform. There are tiny fluctuations, variations of about 1 part in 100,000. These fluctuations represent the seeds of all structure in the universe. Regions that were slightly denser than average exerted slightly stronger gravitational pull. Over time, they attracted more matter, growing denser still. These overdensities eventually collapsed to form the first stars and galaxies. The first stars were different from stars today. They formed from gas that contained only hydrogen and helium, no heavier elements. Without heavier elements to help cool the gas, the clouds that collapsed to form stars were more massive. These first stars, sometimes called population 3 stars, may have been hundreds of times more massive than the Sun. They burned intensely and died quickly, exploding as supernovae and enriching the interstellar medium with the first heavy elements. These heavy elements, dispersed into space, became part of the next generation of stars, which could be smaller and longer lived. Over billions of years, stars formed, lived, and died. Galaxies assembled, merged, grew larger. Clusters of galaxies formed, bound together by gravity. The cosmic web emerged, a vast network of filaments and voids stretching across hundreds of millions of light years. All of this structure, all of this complexity, arose from the action of gravity on the small initial fluctuations present in the early universe. Gravity also determines the large-scale geometry of the universe. General relativity allows for 3 possibilities. The universe could be spatially flat, like an infinite plane. It could be closed, like the surface of a sphere. Or it could be open, like a saddle. Which geometry applies depends on the total energy density of the universe. If the density is exactly equal to a critical value, the universe is flat. If it is higher, the universe is closed. If it is lower, the universe is open. Measurements of the cosmic microwave background, combined with observations of large-scale structure and the distances to supernovae, indicate that the universe is very close to flat. This has important implications. A flat universe will expand forever, but the expansion will slow down over time if there is no dark energy. With dark energy, as we observe, the expansion accelerates, and the universe will continue expanding at an ever-increasing rate. This brings us to the distant future. As the universe expands, the average density of matter decreases. Galaxies spread farther apart. Within galaxies, gravity continues to pull matter together, so the Milky Way and nearby galaxies are not expanding away from each other. In fact, the Milky Way and Andromeda are approaching each other and will eventually merge, forming a larger elliptical galaxy. But beyond our local group, other galaxies recede, and they will continue to do so. In a few 100 billion years, the cosmic microwave background will have redshifted to such long wavelengths that it will be undetectable. The most distant galaxies will have receded beyond the cosmic horizon, the distance beyond which light cannot reach us because space is expanding too quickly. An observer in the far future will see a much emptier universe, containing only the merged remnants of our local group and a few nearby galaxies. The evidence for the Big Bang, the cosmic microwave background, the distant galaxies, all of it will be gone. Star formation will continue for a while, but gradually the supply of gas will be exhausted. Stars will age and die. The smallest stars, the red dwarfs, can burn for trillions of years, far longer than the current age of the universe. But eventually, even they will exhaust their fuel. The universe will enter an era dominated by stellar remnants, white dwarfs, neutron stars, black holes. These remnants will persist for an extraordinarily long time. White dwarfs will cool, becoming black dwarfs cold and dark. Neutron stars will cool as well. Black holes will slowly evaporate through Hawking radiation. But this process takes an incomprehensible amount of time. A black hole with the mass of the Sun will evaporate in about 10 to the 67th years. A supermassive black hole with 1 billion solar masses will take 10 to the 100th years or more. These timescales are so vast that they dwarf the current age of the universe, which is only about 14 billion years, or roughly 10 to the 10th years. On even longer timescales, if protons are unstable, they will eventually decay. The exact lifetime of a proton is unknown, but experimental limits suggest it is longer than 10 to the 34th years. If protons do decay, then all atomic matter will eventually disintegrate, leaving only radiation and possibly exotic particles. The universe will become a diffuse, cold, nearly empty expanse, with occasional photons and perhaps a few remaining black holes continuing their slow evaporation. This vision of the far future is bleak, but it rests on assumptions. We assume the laws of physics as we understand them continue to hold. We assume dark energy remains constant. We assume no new phenomena intervene. The universe has surprised us before, and it may do so again. There may be processes or transitions we cannot anticipate. But based on our current knowledge, gravity will continue to shape the universe, drawing matter together where it can, while the overall expansion driven by dark energy carries structures ever farther apart. Let us now return to something closer to human scales and timescales, because gravity also raises questions about the nature of reality, about what it means for space and time to be physical entities that can bend and flex. In everyday life, we think of space as a backdrop, a container. Objects move through space. Events happen in space. But space itself just sits there. General relativity overturns this view. Space is dynamic. It responds to matter and energy. It curves, expands, oscillates. This has philosophical implications. If space and time are not fixed but are shaped by matter, then the structure of the universe is deeply interconnected. Matter tells space how to curve. Space tells matter how to move. This reciprocal relationship blurs the distinction between container and contained. The universe is not a stage on which matter performs. The stage itself is part of the performance. This also challenges our intuitions about causality. In Newtonian physics, if we know the positions and velocities of all particles at one moment, we can, in principle, predict the future and retrodict the past. The flow of time is uniform and absolute. But in general relativity, time is relative. Observers in different gravitational fields experience different rates of time flow. Events that are simultaneous for one observer may not be simultaneous for another. This does not mean causality breaks down, but it does mean that causality must be understood in terms of the structure of spacetime, not in terms of some universal clock. There are also strange solutions to Einstein's equations that allow for phenomena we would consider bizarre. For instance, the equations permit the existence of wormholes, hypothetical tunnels connecting distant regions of spacetime. If wormholes exist, and if they could be traversed, they might allow for travel across vast distances in short amounts of time, or even travel backward in time under certain conditions. However, we have no evidence that wormholes exist. And there are strong reasons to believe that even if they do, they would be unstable or require exotic forms of matter with negative energy density to hold them open. Closed time-like curves, paths through spacetime that loop back on themselves, are another exotic possibility. If such curves exist, an object could travel forward in time and arrive back at its starting point, effectively traveling into its own past. This raises paradoxes. What happens if someone travels back in time and prevents their own time travel? General relativity allows these solutions mathematically, but it is unclear whether they correspond to anything real. Most physicists suspect that some deeper principle, perhaps arising from quantum mechanics, prevents such paradoxes. The interplay between general relativity and quantum mechanics is one of the most important unsolved problems in physics. General relativity describes gravity as the curvature of spacetime, a smooth, continuous geometry. Quantum mechanics describes particles and fields as discrete, probabilistic, and fundamentally uncertain. These two frameworks are extraordinarily successful in their respective domains, but they seem incompatible at a fundamental level. The problem becomes acute in situations where both gravity and quantum effects are important. Near the singularity of a black hole, for instance, space-time curvature becomes extreme, while dimensions shrink to scales where quantum mechanics dominates. In the first moments of the Big Bang, the entire universe was compressed to a size smaller than an atom. And quantum fluctuations in the space-time geometry may have played a crucial role. To fully understand these situations, we need a theory that unifies general relativity and quantum mechanics into a consistent framework. String theory is one attempt at such a unification. In string theory, the fundamental constituents of matter are not point particles but tiny vibrating strings. Different vibration modes correspond to different particles. One mode corresponds to the graviton, the hypothetical quantum particle that mediates gravity. String theory naturally includes gravity and, in principle, could provide a quantum description of spacetime. But string theory is difficult to test. It requires extra dimensions beyond the familiar three of space and one of time. These extra dimensions are typically assumed to be compactified, curled up so small that we cannot detect them. The theory makes few clear predictions that can be tested with current technology. Loop quantum gravity is another approach. It attempts to quantize spacetime itself, treating space and time as composed of discrete quantized units. In this framework, spacetime has a granular structure at the smallest scales, somewhat like a fabric woven from threads. The theory has had some success in describing the quantum properties of black holes and in providing a possible description of the Big Bang that avoids the initial singularity. But like string theory, loop quantum gravity has not yet made definitive testable predictions. There are other approaches as well, each with its own insights and challenges. What they all share is the recognition that our current theories are incomplete. General relativity and quantum mechanics are both correct within their domains, but they cannot both be the final word. Something deeper connects them, some underlying structure that we have not yet uncovered. This search for a deeper understanding is part of the long history of gravity as a scientific puzzle. From the earliest observations of falling objects to the sophisticated experiments detecting gravitational waves, each step has revealed new layers of complexity. Galileo observed that objects fall at the same rate, regardless of their weight. Newton formulated the law of universal gravitation, showing that the same force governs both apples and planets. Einstein reconceived gravity as the curvature of spacetime, opening new vistas of understanding. And now physicists seek the next revolution, the theory that will reconcile gravity with the quantum world. Part of what makes gravity so compelling is its universality. Every object with mass or energy participates in gravity. There is no shielding from it, no insulation. Electromagnetic forces can be blocked. Strong and weak nuclear forces have limited range. But gravity reaches across the universe. It shapes the largest structures and, we suspect, plays a role in the smallest, most fundamental processes. It is inescapable, and yet, gravity is also the weakest of the fundamental forces. The electromagnetic force between two protons is about 10 to the 36 times stronger than the gravitational force between them. This enormous disparity is puzzling. Why is gravity so weak? One possibility is that gravity acts in extra dimensions, and what we observe is just a small fraction of its true strength diluted across these additional dimensions. Another possibility is that our understanding of what mass and energy are is incomplete, and gravity's apparent weakness is a clue to some deeper structure. The hierarchy problem, as this disparity is called, is one of the motivations for theories like string theory and for the search for new physics at high energies. Particle accelerators like the Large Hadron Collider probe the structure of matter at the smallest scales we can reach, looking for hints of extra dimensions, new particles, or other phenomena that might explain why gravity is so different from the other forces. we also probe gravity directly by testing general relativity in ever more extreme conditions. Observations of binary pulsars, pairs of neutron stars orbiting each other, have confirmed the predictions of general relativity to remarkable precision. These systems emit gravitational waves, and the loss of energy to these waves causes the orbit to shrink over time. The rate of orbital decay matches the predictions of general relativity exactly, providing strong evidence that the theory is correct, even in the strong gravitational fields near neutron stars. Gravitational wave detectors like LIGO, Virgo, and the planned space-based LISA will continue to test general relativity by observing black hole mergers, neutron star collisions, and perhaps other exotic events. Each observation refines our understanding and searches for deviations from the predictions of general relativity. So far, no deviations have been found. General relativity continues to pass every test. But the search for deviations is important. If we ever observe something that general relativity cannot explain, it will point the way toward new physics. Science progresses by finding the boundaries of our theories, the places where they break down or fail to account for observations. Anomalies are not failures, they are opportunities. Gravity also has practical applications beyond navigation and satellite technology. Gravitational lensing, the bending of light by massive objects, has become a powerful tool in astronomy. When light from a distant galaxy passes near a massive foreground object, the light is bent and the background galaxy appears distorted or magnified. By studying these distortions, astronomers can map the distribution of mass in the foreground object, including dark matter. Some of the most detailed maps of dark matter distribution have come from gravitational lensing studies. Gravitational lensing can also create multiple images of the same background object, or even complete rings of light called Einstein rings. These phenomena are beautiful demonstrations of general relativity in action, turning galaxies and clusters into natural telescopes that allow us to study objects that would otherwise be too faint or too distant to see. Microlensing, a related phenomenon, occurs when a smaller object, like a star or planet, passes in front of a background star. The foreground object's gravity briefly magnifies the background star, causing a temporary increase in brightness. By monitoring many stars over time, astronomers can detect planets around other stars, measure the masses of faint objects, and even search for dark matter in the form of compact objects. Gravity is also central to our understanding of cosmic inflation, a hypothetical period of extremely rapid expansion that may have occurred in the first tiny fraction of a second after the Big Bang. Inflation was proposed to explain several puzzles, including why the universe appears so uniform on large scales and why its geometry is so close to flat. During inflation, the universe would have expanded exponentially, smoothing out irregularities and stretching the geometry toward flatness. Inflation also provides a mechanism for generating the initial density fluctuations that seeded structure formation. Quantum fluctuations during inflation would have been stretched to cosmic scales, becoming the classical density variations we observe in the cosmic microwave background. These fluctuations, imprinted on the universe at the earliest moments, set the stage for the formation of galaxies, stars, planets, and ultimately life. Testing inflation is challenging because it occurred at energies far beyond what we can reproduce in laboratories. But inflation makes predictions about the pattern of fluctuations in the cosmic microwave background, and these predictions can be tested by precise observations. So far, the data are consistent with inflation, though alternative models have not been ruled out. Detecting primordial gravitational waves, which inflation predicts should exist, would provide strong evidence for the theory. These gravitational waves would leave a distinctive imprint on the polarization of the cosmic microwave background, and experiments are currently searching for this signal. Our exploration of gravity has taken us from the familiar experience of standing on solid ground to the most extreme environments in the universe, from the everyday to the cosmic, from the beginning of time to its distant future. Along the way, we have seen how gravity shapes the motion of planets, the evolution of stars, the structure of space-time, and the fate of the universe. We have seen how a simple question, what holds us to the ground, opens into a profound inquiry into the nature of space, time, matter, and energy. Gravity remains mysterious in some ways. We do not know how to reconcile it with quantum mechanics. We do not know what dark matter is or what dark energy is. We do not know what happens at the singularity of a black hole, or whether the universe had a beginning in the way we usually think. These are not small questions. They strike at the heart of our understanding of reality. Yet we have learned an immense amount. We have a mathematical framework, general relativity, that describes gravity with stunning accuracy across a vast range of scales. We have observational tools, from gravitational wave detectors to space telescopes, that allow us to test this framework in ways that would have seemed impossible a generation ago. We have traced the history of the universe from the Big Bang to the present. Understanding how gravity has shaped that history at every stage, this is a remarkable achievement, a testament to human curiosity and ingenuity. Standing here now, we are part of a process that began billions of years ago, when gravity pulled together the matter that would become the solar system, the Earth, and eventually us. The atoms in our bodies were forged in stars, scattered into space by supernovae, and reassembled by gravity into new stars, planets, and life. We are, in a literal sense, children of gravity, products of the same force that holds galaxies together and bends light around black holes. And we are observers of gravity, beings who have developed the capacity to ask questions about the universe and to find answers. This capacity is itself remarkable. The universe has evolved in such a way that parts of it, like us, can contemplate the whole. We can stand on the surface of a planet, look up at the night sky, and understand, at least in part, the forces that govern what we see. This understanding is incomplete, provisional, subject to revision. But it is real. Gravity, the quiet force that shapes everything, connects us to the cosmos in ways both tangible and abstract. It keeps us grounded, literally and figuratively. It determines the structure of the world around us and the universe beyond. It poses questions that challenge the deepest thinkers and inspire the most ambitious experiments. It is a force we live with every moment, yet it retains the power to surprise us, to reveal new depths, to remind us how much we have yet to learn. We stand on solid ground, held by gravity, part of a universe shaped by gravity, seeking to understand gravity. The journey from the first simple question to the frontiers of current research has been long and winding, filled with insights and puzzles, triumphs and mysteries, and the journey continues. Each answer leads to new questions. Each observation refines our understanding or opens new avenues of inquiry. The quiet force that shapes everything remains, as it has always been, a source of wonder and a challenge to comprehension, inviting us to look deeper, to think harder, to never stop asking why.